coordinate system, right? So now there we said, so this would mean that Vz equal to Vz of xy. Of course, there the x was this direction, so we said neglect the dependence on y. That I pointed out, if you analyze the equation of motion through a dimensional analysis, you would find that that is justified if the width of the channel is much larger than the height of the channel. So we can neglect the velocity variance in that direction. Here that direction is x, right? So we would effectively have to mean for the rectangular channel is that Vz would be a function of y alone. So in all the expressions we had, the Vz was a function of x, you have to convert that to Vz as a function of y if you want to compare it with how that would differ now. But here that approximation is no longer valid because it's a triangle now, right? So the width is also fixed actually. The height is h, width is 2h over root 3. Width is also varying actually with the position, right? The maximum width of the channel is 2h over root 3, which certainly is not much different from h, right? So that approximation will no longer be valid. So the only difference that would come will be in the equation of motion, which would read like this, minus dv by dz. Look at the equation of motion in the z direction. You would now have to consider the dependence of Vz on both x and y. Now I have modified the statement slightly. So now the same, now dv by dz, we have seen that dv by dx is equal to 0, it will turn out to be 0, and dv by dy would be minus rho g, right? So p would be minus rho gy plus some function of z. So dp by dz would simply going to be p naught prime of z, which is the same quantity we had in the earlier discussion on flow between two parallel plates, right? So I can write this as mu times d square dz by dy square is equal to dv by dz, which is simply p naught prime of z. So again, the same argument which we made, right? This is this is equal to 0 actually. dv by dz is p naught prime of z, right? So that is clearly the same argument holds what we had earlier. The left hand side is a function of x and y alone, the right hand side is a function of z alone. So I can follow the same idea and equate this to a constant. But now the solution of the problem is made difficult by the fact that the no-slip boundary conditions, right? So you would have to imagine the solid surface is both inclined as well as on top, and the fluid is flowing in between, right? So what would the no-slip boundary conditions be? So y is equal to 0 on the top surface and all along the inclined faces, right? So that's what birds would like to, if you see, this is a new coordinate system, but it's not quite a coordinate system. It's simply that this would be easily shown to be represented by y equal to root 3x, and this is given to be minus root 3x. So the no-slip boundary condition is Vz is equal to 0 along y equal to h, along y equal to plus or minus root 3x. Okay. Now it's not clear how we would go about solving this problem, but certainly a plausible solution is given in Wordsworth Lightfoot, and that's what I have also given in the assignment sheet. And that would be Vz is equal to some alpha times y minus h times y squared minus 3x squared. This you can propose as a plausible solution that satisfies the boundary condition, right? But there is no guarantee that it should satisfy the equation. However, if you substitute it into this equation, mu times d squared dz by dy squared plus d squared dz by dx squared, you will actually find that that is a constant. It will turn out to be a constant. If I call this constant, let's say as this constant is P naught prime Z, so we will find that P naught prime of Z is equal to minus 4 mu alpha times H. Right. So that is what you have to verify. What I am saying is, I have given you an expression of Vz. Alpha is assumed to be a constant, which means it's independent of x and y. That's what it means here, right? So I have to calculate d squared Vz by dy squared, and I have to calculate d squared Vz by dx squared. Those are easy to calculate. If you substitute it in, then you will get mu times d squared Vz by d squared Vz by dx squared plus d squared Vz by dy squared to be equal to minus 4 mu alpha h. You can easily verify that. That's clearly a constant. The alpha is a constant, mu and h are also constants, right? So from which I can calculate alpha now to be P naught prime of Z, that means minus, that will be the negative of the pressure gradient in the Z direction, that will drive the flow actually by 4h, and all I have to do is to complete the solution as if you compare it to what we had in the the rectangular case, and this is to be modified. So there it would have been y minus h times y, now it would be y minus h times y squared minus 3x squared. It's not quite separable. I mean, this equation you cannot possibly solve by separation of variables because of the complications given by the boundary condition. Clearly, it's not a function of y times a function of x. Right? It's sort of coupled, the dependence on x and y. So this we may conclude as the solution. It's not a rigorous solution of the equation, but we propose a plausible solution that satisfies the boundary condition and verify that it satisfies the solution. Right? So, are there any questions on this? Then the mass flow rate. How will you calculate now the mass flow rate? Rho V dotted with N dA. Now V is Vz Ez. What about N? It depends on where you look at it. If I look at it at the entry point, N would be minus Ez, but I can look at it at the exit. Then N would be Az, and I get the mass out at the exit. Right? So that would also be Ez. It's very straightforward. And dA is simply dx times dy. Right? That is the corresponding dA for n equal to Ez. So nothing changes actually. But the only thing that would change are the limits. It's no longer a rectangular domain. So what would be the limits?
3x 2h. Root 3x 2h for y.
Yeah, y weight. So what would be the limit? So I can put this as y equal to x equal to. What would you could do it either way, because what we have to describe, that will be this domain. You have to represent in terms of limits. Now there are many, well, at least two ways of doing it.
Y equal to minus h by root 3 minus root 3 minus h by
x equal to minus h by root 3 to h by root 3.
minus root 3 to plus root 3.
Can you write the limits? You should know how, this is standard. This is a very easy problem in the sense it's an area integral on the plane. That makes it much easier. The area integral on 3 dimensions, that would be more difficult. So you have to describe the domain clearly. The domain is what I have given as a shaded area that has to be covered, right, through limits on x and y. It's a standard problem in 2-dimensional integrals. So y equal to x equal to, that's 2, x equal to minus h by root 3 to plus h by root 3, that is certainly correct, right? And y equal to 0 to h, that's correct. That's one way of representing the limits, but it can also be represented. Suppose, see, now how do we calculate the integral? So the integral would have to be done in two parts. First I will, because the y limits are the constant limits. See, both y, for a rectangular domain, both y and x limits would be constant. That's the easiest to do. Here, right, in such cases like this, one of the limits can certainly be expressed as constant. The other one depends on x or y, right? So I would have to here calculate the integral over x first and then the integral over y. So when I integrate, I would have to simply treat y as a constant when I first integrate with respect to x. That's a perfectly justified procedure. Another way, suppose I want to put the x limit as the constant limit.
Minus h by root 3 to h by root 3. X limit. Constant.
Oh, that is what, no, this is not quite correct.
It's minus y by root 3
Sorry.
to y by root 3.
Yeah, what you have written is not correct because both limits can, that would describe a rectangular domain, right? What you have drawn is actually y equal to 0 to h is fine, x equal to minus h by root 3 to h by root 3. This is the domain you have described. It's a rectangular and not a triangle, right? So
Minus y by root 3 to y by root 3.
Minus y by
minus
minus y by
Minus y by root 3 to y by
minus y by root 3 to
plus y by
y
root
by
3.
root 3.
yeah, that might be correct. Yeah, that's fine. I think that is correct. Yeah, that's true. So you can do it the other way also. Suppose I want to put the x as the constant limit.
X will be minus h by root 3
By
to
root
plus
3,
h.
then you would get what you have, minus h by root 3 to h by root 3. So then I have dx here, and y would vary from,
Root 3x to h. Root 3x to h.
yeah. Oh.
Minus root 3.
Root 3x.
No, y is
Minus root 3.
varying like this.
No, no, vertical direction.
Yeah.
Root 3x or minus root 3x to h.
Y varies from,
Root 3x to h.
that's not what I think then you would have to split it because this is minus root 3x. So for the range between minus h by root 3 to 0, y would vary from minus root 3x. So I may write it in two parts. Then y would vary from minus root 3x to h. Because the two equations are different, right? Because this is y equal to minus root 3x and this is x, y equal to plus root 3x. So for the part where x varies between minus h by root 3 to 0, y would actually vary from minus root 3x to h. And that would cover this domain. The other domain would be covered by x is equal to 0 to h by root 3 and then y would be root 3x to h. So it seems to me that this integral would probably be easier to estimate. Maybe we have to do it, this got the right answer, this seems to be correct. Right, x equal to, yeah, there's no problem at all, right, because I think so you can write either of the two ways, both of them should lead to the correct answer. One of them might be more tedious than the other, that you can easily verify. The answer turns out to be MR is minus P0 prime z by h power 4 again we get 60 root 3. That is what you should get. That's the answer I don't know if words will ever have given the answer, but this should be what you get. Whichever way you split the integral, you should get this. So this sort of gives. We still have some time left, and quickly survey the other problems. Problem number 2 is what again we require the torque. And the reason why problem number 2 is given is the parallel disc viscometer, which he says is used to calculate the viscosity. It's probably worthwhile just looking at it. How to calculate the viscosity of a fluid in a parallel disc viscometer, where again I have two plates and there is a fluid between the two plates, right? So, but however, the top plate is, he's saying, rotated with omega. So it's sort of a d-phi motion, but now the fluid is between two plates rather than between two cylinders. Right? So this is what we say is the parallel disc viscosity. These are the two parallel discs, right? And then he takes, I think, the z-axis, he probably takes it to be this at the bottom. The origin is taken here, and so this is the z-axis, and this distance is given to be p. Here again p is equal to d phi d phi. Right, and so the continuity equation would be that d phi by d phi is equal to 0, and d phi is equal to d phi rc times z. And words were Lightfoot simply asks us to assume. He asks a question, I mean, what is the justification for this? I can't really, give an obvious justification, but certainly this is what you are asked to assume. Right, so again, we have to assume that dt by d phi equal to 0. And then the p would turn out to be p naught minus rho g z. And the important equation would be mu times d by d rc, 1 over rc times d by d rc d phi plus equal to 0. That is the equation. Now this does not necessarily mean, I have been able to attempt to prove that this necessarily means that this is a function of rc times f of z. Probably more generally, we can assume that the solution, this is probably certainly solvable by a separation of variables, because here the domain is fairly fixed. Rc equal to 0 to r and z equal to 0 to b. Separation of variables, you might be able to show that actually this has this form, right? You have to set it up as an eigenvalue problem, and I got to the stage where you have to show that the eigenvalue problem is valid only for lambda equal to 0. That's what it comes out. I have not really carried out the full solution, but nevertheless, if you substitute this form instead of e times rc, you just substitute rc times some function of z, then you will get the striking result that e squared f by dz squared is actually 0. Very simple solution if you assume this form. I am not very sure if it is general or it's an approximation or this is the only form allowed, and I will leave that for you to decide. Those who have better skills in mathematical methods can probably justify this, but this will imply that f is equal to some c1z plus c2, right? And if I now apply these boundary conditions, clearly since because it's the product of rc times f, right? So dc is d phi is 0, f must also be 0. So the boundary conditions are z equal to 0, d phi is equal to 0. at z equal to b, d phi will simply be RC times omega. Maybe that is why he says that this form is justified. Is probably inferring it from this form of the d phi at the boundary. Right? That is one way of arguing why we should assume that form, or why that form is justified. But nevertheless, if you substitute this in, we will simply get a simple expression that d phi is omega RC by b times z, because the bottom plate is not stationary. Right? Now the torque, if you do the analysis properly, as I said, again x cross d dA cylindrical coordinate with now d phi, it is a function of RC and z actually, both of them. If you do that, then you should get the following formula for the torque. The z component alone will survive again. It is 0 to y, it is 0 to r, but r is the radius of the cylindrical plate of this. Right? What you should get is Ez phi RC. Everything is happening here at z equal to b, because that is where the fluid is in contact. That is the torque that is applied to the top plate to make the fluid rotate. Right? So this would be at z equal to b, and then we have the integral is over RC and phi, and you get this result pi mu omega r power 4 by 2b. Whether you know how to calculate the torque in the general case or not, certainly if you just obtain what Ez, that I would leave as an exercise. You should find out at least what Ez phi is, right? And then go back. This can be assumed as a linearly viscous fluid. You can find out what Ez phi and how it is related to the derivative of d phi, right? So then the point he makes is that this is the torque, and so the viscosity can really express in terms of the z component of the torque. That's the only component that would exist in this case, 2p by pi omega r power 4. So by measuring the torque, what Birch would say that this is the way of measuring the viscosity. We measure how much torque mechanically we should apply to rotate the top plate with some angular speed omega, which is also can be measured, right? And then how much torque we should supply, and then we can determine the viscosity. But it goes with all these approximations. So if these approximations go through, then this is a good way of estimating the viscosity. Right? Now the third problem, radial flow between porous cylindrical shells. Again, I will let you do the problem. Right? Here again, the assumption that Birch is asking you to make is VRC is independent of phi and z, and that's not what the continuity equation says. Continuity equation only says that RC times BRC. Third problem in assignment 4. RC times BRC is actually a function of phi and z. So we are saying that BRC is independent of phi and z, and there is really no obvious justification for it, then this simply has to be a constant. This is asking you to assume. That's not what the continuity equation tells. Right? They don't tell that RC and BRC is a constant, but rather they say that it's a function of phi and z. So I sort of modified the problem to say that it is a function of phi and z, just assume it. And then you can go ahead and solve the problem. This is again a flow between of a fluid between two cylindrical shells, but it's a radial flow. So it is sort of complementary to the earlier case where we had the cylinders being rotated with constant angular speeds and d phi was dominating, and we had the case of two parallel discs like this, right, where there was a radial flow. So these two problems are complementary. Here you have the top plate being rotated, so we sort of have a angular flow between two plates, and contrary to what we considered earlier, the fluid between the cylindrical shells, we are having a radial flow. He says that is possible if the cylindrical shells are porous, and he assumes only the radial flow is dominating. So I will let you solve the problem and get the result. So the V is very simple. VRC is simply already known. C by RC. What he is asking you to get is if you leave C as an undetermined constant, it will be known. For instance, if I know velocity at any one of the boundaries, right? So then you have to calculate the pressure profile. He has given some expressions to calculate the to justify and get the pressure profile. So I'll let you do that. But I have the answer to that pressure. The modified pressure can easily be shown to be simply rho c squared by 2 by 1 over rc squared minus 1 over r squared. Then r is, I guess, the radius of the outer shell. We take it r to be the so this is what you get. That's very easy to derive. So this is almost that the velocity is given. We have to calculate the pressure profile. I'll just briefly comment about the last problem. Even though I thought it might be useful illustration, finally when I solved it, I had to find much to comment on it. But the important thing is that you should here to have a flow. The idea is of obtaining the solution. So this is the x. Now x is the flow diagram. What he's saying, this is a slit, and then you have fluid coming in here, right, and then flowing into the slit. And so he gives 2 or 3 different expressions for the velocity. The velocity that profile that we would obtain as a one-dimensional velocity profile, right? That would be far from the inlet, is what he says. Dx is a function of y. But in the region leading to the inlet and in the region, close to the inlet, he actually says this would be a 2-dimensional flow. Dx and dy both would be non-zero, right? So he gives the solution. So he has derived the expressions using the cylindrical coordinate system in the next problem in the book, but I have not discussed that. But the expression he has given is what he is asking is certain questions about the shear stress and the momentum flux tensor, right? Now the momentum flux tensor is given by rho v, right? So what would the momentum flux tensor be in Cartesian coordinates? Right? It would be a tensor, and it would have rho times dx square, dx dy, and so on, dx dz, and so on. So what is the meaning? We have seen the momentum flux tensor is actually useful in giving the momentum flux vector, right, across a certain area element at a given point, right? So you can ask, he asks you to calculate, for instance, rho vx squared, rho vx dy, and so on, and make some inferences from that, right? So what is the interpretation you can give to these terms? That is the only question I want to discuss in the few minutes we have, right? So the question really is, what does this mean? Rho vi dj. What can you mean? The meaning you can give to this. So it has two indices, it's a tensor. So what can you say about the
Stress on a surface perpendicular to I direction due to momentum flow in J direction.
it's not strictly a stress, it's a divergence of this that is sort of, you could say that, yeah, but it's not quite. I would like to distinguish between the stress is something that directly deals with the force, whereas this is just a momentum. So the two are related by the equation of motion, right? So if you want to, suppose I can write the tensor in this manner. Right? Suppose I write the tensor can be written in this manner. Suppose I take the dot product with some arbitrary unit vector Ek. It can be any vector. What we normally do is calculate rho B dot at an n. The n can be arbitrary. Then we say that to give the momentum flux vector, right, across that area element which has the outward unit normal n. But if you want to give an independent or a meaning to each of the components of the tensor, then I would consider, just as we give the meaning to the components of the stress tensor, right? We could consider dot product with each one of the Cartesian unit vectors, but k can be 1, 2 or 3. Now what is this equal to? Right? This is equal to rho Bi Bj. Ei Ek dot Ek is Ei and delta Jk. Right? So this would simply be rho Bi Bk Ei. Right? Now I will write this as rho Bi Ei multiplied by Bk, because I want to bring out the importance of K. Because K is, you can regard, so what we can regard is at a point, right? I can define B. I know what rho is, so I can calculate what rho BB is. Now suppose I consider an area element whose normal, outward normal is, let's say, in the Ek direction. Right? So now this tensor, right, is going to now give a vector that will calculate. So what I am calculating is rho BB dot Ek, that has to give a vector finally. That's the momentum flux vector. So if I know that, then if I consider an area, a whole area, each point, if I calculate this, I will get the net momentum flux by integrating over the surface. So that's the meaning of the momentum flux vector, which is what is of practical interest, right? So from this, I can regard this can be itself. What is rho Bi represent? Rho B, this is nothing but rho B. This represents the momentum density. This units of momentum per unit volume. So that gives the momentum density at that point, right? So what this says is that rho Bi Bk, what can you say about that? Right? Because I want a particular element. I started because I use J here as the summation index. I am getting a meaning for rho Bi Bk can be regarded as the ith component of the momentum flux vector. The whole thing, rho Bi Bk, right, across an area element whose normal is outward normal, that is along Ek. Right? So if I specify, so I am given this, I am specifying a vector, right? Ek, let us say. If it is Ek is, if k is equal to 1, right? I am getting the three components of the momentum flux tensor a vector rather, right, across an area element or emanating from an area element whose unit normal is in the E1 direction. So I think then I would have to tell you rho B1, B1, it would be rho B2, B1 and rho B3, B1. So I will get interpretation for three of the elements of the momentum flux tensor. Right? So by considering k equal to 1, k equal to 2 and k equal to 3, I can give an interpretation to all, each and one of the 9 elements of the momentum flux tensor. Right? You can interpret it in this way. But however, this is a symmetric tensor. First of all, rho BB is a symmetric tensor. The rho BI, BK can also be written rho BK, BI. So the interpretations are interchangeable. I can interpret it in any way. The indices I and J, right, can be interchanged, and I can get a different interpretation that will also be valid. Either I can look at the first index as here, right, corresponding to the I component with the normal along EK, but since it can also be written as root EK times BI, the converse interpretation is also possible. Right? So both ways you can interpret it. But as you pointed out, one is certainly the momentum flux density at a given point that will correspond to one index. The second index will correspond to the area element, because what we are looking at is getting a tensor from a vector. Right? The tensor merely serves the purpose of getting you the momentum flux vector, which is what is of utmost importance. So in this way, I can give a meaning for each one of the 9 components. Now we can simply evaluate these components for the example that is given here, and you can find out what is happening depending on the sign, whether it's positive or negative. You can make inferences based on that. So I will leave it at that. Are there any questions on the assignment problems or on any other matter covered so far? So you can think about it. We'll discuss briefly any questions that are there at the beginning of the class on Thursday. Otherwise, as I pointed out, whatever we have covered until today is included for quiz 2. Right? So we are done with quiz 2. We start on a new topic starting from Thursday.